So first of all, it's my pleasure today to present this ongoing project in our group. It's about a security protection for wearable devices to defend spoofing attacks, where we utilize the signal variation coming from human body movement in the physical layer to distinguish the attacker. And as an introduction, I'm Wenqing and I'm second year PhD student in Uppsala University. So let's start. So first, I will guide you to some background information. And I believe most of people here is familiar with wearable devices, so I will more focus on the application scenario our system targets, the physical layer attacks we concern, and also the research challenges we met. And first is some market data, which is about how many wearable devices in the market. So for this, we can easily say wearable devices market is growing really fast. So, but what kind of devices we call them wearables? For sure, I think it covers some daily usage devices such as smartwatch, earphone, fitness wristband, and so on. However, it plays a more important role in medical field. Doctors always want more information about their patients, and real-time monitoring is essential for doctors to get first-hand information about patients, especially for chronic diseases. So not only, and also not only sensors, these applications also involve actuators, such as drug delivery devices. The combination of sensing and processing with an actuator like drug delivery devices is an ideal blueprint for next revolution of healthcare system. And diabetes is a good example. So you can see before this is a daily life of diabetes patient, but now with an automatic wearable system, which including a continuous glucose monitor and also an insulin pump, this kind of combination totally changed the patient's life. And not only that, doctors also can benefit. They can get more information, do remote diagnose, and even execute some treatment remotely. And similar story also happens in many other diseases. And our project is focused on looking at the security part of this kind of medical real-time monitoring system. And we know like this kind of medical system is life-related, so security is for sure really important, but the security protection is left behind a lot. Research shows that wearable systems are exposed to massive cyber attacks such as man-in-the-middle, data breaches, ransomware, and denial of service, and also spoofing attack. And medical wearables raise a potential data privacy and security concern for the users. So they are the potential pose a risk to serving as a launching pad for attackers directed at healthcare entities. And even more terrified, like I mentioned before, this system also has the possibility to threaten human safety and life. And one of the dangerous security threats is device spoofing attack, because it happens in the fundamental layer of network stack and can be exploited to launch many other sophisticated attacks, which also can mean like in many other more advanced attack. In the attacking chain, the spoofing attack actually is the step one to boost this kind of attack. So what is a spoofing attack? What is device spoofing attack? It is malicious party Eve, which impersonates another legitimate Alice and with identical SSID, MAC, or IP addresses. And why this attacker is possible? Because device identities like MAC or IP addresses are artificially configured information, so they can be changed. They also can be forged. And only with this kind of plain IDs is too naive. So there is also authentication protocols to enhance the security. But these protocols have been proved insecure and broken. For example, this year, SMP researchers break the newest WPA3 protocol for Wi-Fi device authentication. So based on this kind of situation, spoofing attacks can forge these identities, also can compromise authentication protocol easily. What can we do about it? We know, like, to defend spoofing attack, this kind of attack happens below data link layer, where attacker directly forges IDs like MAC or IP, and any higher layer mechanisms still based on these IDs are useless. So a better way is using the physical layer features to support it. And physical layer features are the signal characteristics in wireless channel, which are difficult to modify at will, because like in Professor Lee's mentioned, in wireless world, signals which are electrical magnetic waveform are transmitted by the transmitter passing through the medium and arrive at the receiver. When there is two transmitter transmits the same signal at different locations, the signal arrive at the same receiver shows different characteristics. And because there are two different channels, and in these two different channels, signal is be fade away or be scattered, be reflected by surrounding environment in different ways. So several features can be extracted by the received waveform, which carries information to describe the signal behavior and can be used to distinguish different transmitters. And signal strength is one, which is a power level of received frame measured at the receiver antenna. We also call it RSS. And all existing research use RSSI for spoofing attack requires a measurement from several access points in a stationary setup. But in wearable system, human body movement makes it impossible to apply existing methods to distinguish spoofing attacks. Moreover, wearable devices are generally designed with limited resources. Security systems that require either multiple supporting devices, a large amount of data, or heavy computational algorithms are problematic. So we need a new solution to solve this problem and suit for this new scenario with moving devices. And also, we don't want to add up any extra devices, and we prefer a lightweight system. So these are three requirements, also the research challenges in our project. And here is our solution. We name it PHY-IDS, which is a physical layer detection system, especially to detect spoofing attack for wearable devices. And the ground truth behind is devices are worn or implanted on our bodies, but at different locations. When we are moving, they are also moving with our bodies. So the signal features will follow the movement patterns. Different transmitter and different locations will have different patterns. With body movement, the RSS behavior of off-body devices differ from on-body devices, and the on-body devices at different positions also different from each other. So this diversity in future dynamics is used to identify the signal source. And for attacker which is at another positions, for example, the off-body attacker here, it is hard to fully follow the legitimate user channel patterns. And we use it to detect and filter out the signal coming from the malicious devices. And here it's easy to see, our system has two tasks. First, you need to analyze the legitimate RSS time series, tracking the legitimate signal behavior and learn the good patterns to predict what will be the next upcoming RSS sample. Then you need to detection process to check if the real upcoming samples is fulfill the regular patterns or not. So based on these two explanations, our system mainly have two parts. The prediction part uses an autoregressive model as a time series prediction models, which we call it small f here. And the task of this model is to predict upcoming values, which we call it small x at time point I, small x hat I, with a lagged record in a size and sliding window, which is a big x minus 1. And the function f is trained with the historical RSS traces collected in the training step. And here, in this piece of work, we compare two representative models in time series analysis. One is linear autoregression, which is lightweight and suited for linear relation dominated data. And another is one type of recurrent neural network, which is good at nonlinear modeling for long-range sequence prediction. And after we have the estimation value, we pass it to the detection modules, which compute the error between prediction value and also the real observed sample value as a normal scores for every frame. And alarm is triggered whenever the error is higher than the threshold theta. Here I want to mention that our paper, this workshop paper is more focused on the prediction part. For sure, you can use more advanced anomaly detection algorithms, get improved performance. And after we have the majority two components, so here is our system overview. The system contains 4 steps. collecting training time series in step 1, and training the model in step 2, and the complexity of the model training is considered too expensive for resource-constrained devices. So we execute the step 2 in a more powerful device such as a hub here. And then step 3, the individual wearable devices download back these models, and real-time detection runs locally, ensure timely detection in step 4. And normally, the naive spoofing attack only attacks step 4, which try to spoof the target devices blindly. But most advanced attacker might also exist in the deployment of the previous 3 process, including the training process. And also, they might have the learning capability which can train their own models. So based on this idea, based on the real attacking risk, we consider 4 types of attack with increasing knowledge of the deployed detection system in our attack models. So there is some basic assumptions. So first, this is how our system normally is working. So we estimate what should be the next value when the upcoming signal is really coming from the legitimate users. Then it will follow the patterns and have a smaller arrows. When it is not, then the attacker, then it's not fulfill our regular patterns, which has a large error ratios. So naive attacker just blindly sent out the package with a default setup and use fixed transmitting powers. But smarter attacker, they will try to guess what will be the X within the boundary. But it's inefficient, they just randomly guessing. So a better way is to, based on some knowledge, they can listen or they can know and to do some reasonable guessing. And what kind of information they can get. We need to remember, wireless medium has the open nature by default. So everybody can eavesdrop the same traffic from another positions. Then they might also have different level of knowledge about the deploy system. For example, they might have our system used the well-trained prediction model, and some might even have the raw training data. And besides that, they might make use of the above 2 informations or several information together and with some learning capabilities to make good guessings. And after they have the good guessings, they can change their, adapt their transmission power to matching these values. But they also have something which attackers cannot do. For example, at least the target receiver should not be compromised. Otherwise, we don't have the spoofing attack, basically. So based on these assumptions, here is a detail of the 4-level attacker. The level 1 for sure is the most naive. They don't know anything and they cannot transmit the transmission power. But the level 2 attacker, which can hack the model deliver process and steal the well-trained model. And also they can adjust their transmission power for sure. And the 1 level up, the level 3 attacker emulates the step 1 data collection process on another person, which can help them get the mimic version of the trained data and train their mimic version of the prediction models. And the 1 level up, the most strongest attacker in our attack model is the training data stealing attacker, which is in the data collection process, they also eavesdrop the same signal, but from another positions. And also they steal the training data at step 2 to train their own real version of prediction models. So in our model, we evaluate how good these different level attackers can make the good guessing. And after we introduce the basic content, and I will directly go to the evaluation part. So first, I will introduce our experiment setup. We tried several environments. Here we only show the most challenging one, which is indoor office environment with regular furniture and lively wireless environment, which I mean Wi-Fi and Bluetooth signal also coexist in this 2.4 gigahertz bands. And we set up a wearable system prototype with 6 flight modes. 3 of them are proxy for wearables, 1 on different body area, like the green dots here, and 1 as hub fixed on the wrist. And another 2 is attacker, 1 is on body, another is off body attacker. And in the experiment, 2 volunteers participate, and for data collection, we ask them to wear the modes and work about 10 minutes randomly in their normal way. And to evaluate, we evaluate the prediction part and detection part. For the prediction part, we use normalized mean absolute value, which is the absolute difference between estimation value and the real observed value divided by the real observed value. So we will show it in percentage. And in order to test how much data is needed in our sliding window, we also, to get to good prediction accuracy, we also resample the data into different sampling frequency from 1 to 200 Hertz. And in our detection part, we just use a common use accuracy to evaluate our performance. And first is going the prediction. So here is two figures. The y-axis is error ratio and the x-axis is different sampling ratio. And also we compare the two model performance with the data collected from different body positions. And mainly I want to summarize as the following 4 questions. So the first one is if the model can capture the time series behavior and how good the accuracy is. So basically, the major error ratio distributes around 2 to 7%, and the best can reach 1%, which indicates an average accuracy of about 96%. It means both models can nicely capture the mapping between historical data in window and also the current samples. And next question is which model is better? In general, it's clear that autoregression performs slightly better, so we can see the lines here. And this can be explain, like maybe there is 2 potential reasons. First is the linear relationship dominate in our data. And also another one is we know like neural network has really high parameter space. So it's really hard to traverse to find the best combination. So in some situations, it has slightly worse. And also we compare the training and prediction complexity about these 2 models. Normally, for sure, the autoregression model, it has a lower cost with comparable performance. So in the following experiment, we are just show the autoregression model performance. And also, next question is how much the sampling frequency matters. First, the sampling ratio increase, the prediction error decrease. That's because high resolutions give us more information to get better predictions. And another is we also find there is a rapid growth on the 20 Hertz. That can explain use some Nyquist theorem, Nyquist-Shannon theorem, because when our sampling ratio is lower than 2 times of the phenomenon ratio, it's hard to get enough information to capture the fully phenomena. So normally human body movement is around 2 to 10 Hertz. So like a frequency under 20 Hertz, it's difficult to capture enough efficient information. And also the final question is, does the sensor placement matters? Sensor placement has influence, but it's still within the range I mentioned at the beginning. So, and after we see the prediction part, we go to the detection part. These 4 figures show the capability of our system to detect 4-level spoofing attack we mentioned before, and we use 10 Hertz sampling ratio here. And the box is an arrow, also the abnormal scores I mentioned before, statistic, and also we mark the individual detection accuracy for each scenario and is on the top of each box. So to conclude, as a benchmark, our system can detect naive attacker with good accuracy. And the 2nd-level attacker is also easy to detect because the model is trained for a specific channel. The where trained models steered by the attacker does not fit where with the physical feature time series which attacker eavesdrop. And 1 level up, the level 3 emulates the attacking setup on another person's helps, but entirely for our system is still impossible. And also training data stealing attacker is considered the strongest. It has information to train his own models, mapping the eavesdrop data with the legitimate data. However, it's still detectable by our system with accuracy around 81. There is a potential reason behind is the unknown channel behind the attacker and the receivers, even when they know what the signal features within the boundary, but they still cannot make the channel estimation and also the channel tracking, and so to manage to adjust the signal to matching that values. So here is all the content about these papers. To conclude, we'll focus on the real-time monitoring system for medical usage. And also we propose a real-time spoofing attack, which is a cheap way to augment the wearable device's accuracy. And we leverage the physical layer signal behavior to distinguish between legitimate and malicious attacker. And we also propose four-level attacker models based on the real attacking scenarios, and we show considerate like accuracy to defense different kind of spoofing attack. So thanks a lot. This is all my presentation, and that's all.